My talk today is about hindsight bias and how to deal with label leakage at scale. So I'm a senior data scientist at Salesforce. I work on the Einstein team, the Einstein platform team, where we mostly work on automating machine learning at scale. And to kind of just give a brief introduction of like what Salesforce does, to kind of give you a background of where all this data comes from and what the problems are that we deal with. We have a CRM company and we have a ton of data, a ton of different kind of data. So we have over every day, more than 3 million new opportunities get created, 1 and 2 million leads get created, and this is every single day. And currently Einstein gives about 3 billion predictions a day too. So just to give you an idea of the scale that we have to deal with here. And also, even though I assume most people here are familiar with the typical machine learning pipeline, you do your ETL, you do some data cleaning, then you engineer your features, you do some model training and model evaluation. This is a cycle that go on until you're happy with how your model performs, and then you deploy the model in some shape and form. And once it's in production, you score and updates the models, give scores with whatever frequency you want, and update the models when necessary. And of course, this is there's only a cycle between the training and evaluation here, but of course you go back and forth between different things. Sometimes you go back to the feature engineering, sometimes to go back to the data cleaning and so on. And the problem that we had is that, well, in our case, we don't just have one customer or one use case, we have hundreds of customers. And each customer has multiple use cases. So you have to multiply this pipeline by the number of customers and the number of use cases. So now you don't have one pipeline, you have hundreds of pipelines. And this is problematic in our case because, well, there's simply not enough data scientists to work on each of these models and hand tune it and go through this pipeline individually, right? So we also don't know often the specific use case of the model. So every time a data scientist would work on a model, you would have to sit down, learn about the company, you learn about the data, and then try to build the best model. So the conclusion that we had here was that each step in this pipeline that I showed you had to be automated, because otherwise you just can't really deploy anything at Salesforce. Another problem that we had is that the data is very messy that we get. So if you work for a company where you collect your own data and you produce that data, you have some control over how this data gets generated and how what shape and form. For us, well, the data comes from customers, right? Customers who use Salesforce, and no one really likes data entry. So a lot of this data it's manual data entry. So often there's missing fields, someone doesn't fill in the field correctly, or there's typos, so you have a string that 99% of the time matches another string, but not quite. There's 1 or 2 typos in them. You also have automated business practices. So not everything is manual. You have some practices that where fields get generated automatically or get filled in automatically. Someone fills in an email on a form, all of those fields then get populated in Salesforce. And this is also problematic sometimes because depending on who fills out the form or where this form comes from, there will be patterns in the data that for you, when you just look at it, you don't really know why this pattern exists. But if you know who generates this data and how, you realize there's some kind of pattern in there. Also, Salesforce is very customizable. So think of it as a giant spreadsheet where you can add columns and you can remove them, or you can just not use them at some point. And we have customers that have 600 to 800 columns. And it doesn't surprise you probably if I tell you that not all 800 columns are used at the same time for every single row. Another problem is that we usually don't have any historical data. So this means that for each of these columns and each of these fields that I'm talking about, we don't have a change log of all which value gets updated when. It's impossible to keep track of that. So we only ever get the data at a snapshot time. This is, as of today, this is what the data looked like. We don't know really what it looked 5 minutes ago unless we also happen to pull the data 5 minutes ago. Which means we have a big cold start problem. We get the data, we only know like, hey, this is what it looks like now. We can't really go back and see what happened before. So this was just kind of to give you a background of like the type of data that we deal with and kind of like what some problems are with it. And the reason I'm giving you this background is that this really led to a lot of hindsight bias, or also known as label leakage or data leakage, where really we have this massive problem of messy data that leads to this. And so what is label leakage? I'm using an example here from Back to the Future, the second part, which is a little more unknown. But basically here, Marty McFly travels into the future. He obtains the sports almanac, which has all the results from all the sports games from like, the future. He goes back in time, he loses it, some guy picks it up, and he bets on all the games. And he obviously wins every single time, which is great for him, but creates a lot of problems in the universe. So that is basically what label leakage is. It's knowing things that you shouldn't know because they actually happen in the future. So to give you an example, which is very classic, it's using the Titanic dataset, which I assume most of you are familiar with. It's something you can get from Kaggle, except what they don't tell you on Kaggle is that there's several columns missing, which I will go into later. But what you're doing here is just predicting the survival on the Titanic. So what you can see, it's very easy. There's some very straightforward kind of like statistics here. Is if you're male, you had a higher likelihood of actually not surviving. If you were a female, you had a higher likelihood of surviving. If you were in first class, this is also like all not super surprising, but if you're in first class, you also had a higher likelihood of surviving compared to when you were in third class. Right? This is all very straightforward. This is all something you can kind of like tell when you do exploratory analysis. So now what they didn't tell you when you got that data set on Kaggle is that there was also this column here, which was it's called a body number. And when you look at it, and you look at when this column is filled out and when it's empty, so it's a numerical field, but when you look at it, you see, is there a body number present or not? What you realize is, well, if the body number is filled out, you didn't survive. If there isn't one, then 58% didn't survive. So a body number is simply, when you look at the description of the data, it's kind of macabre, but it's basically they assigned you a number to your corpse when you died. So obviously, when you have a body number, you died. I really should, look at some less macabre data sets for next time. And there's a similar column here, which is the boat number. This is the boat, this kind of like the boat that you were on when you got off the ship, right? So here again, when you didn't have a boat number, 97% didn't survive. It's not quite as straightforward as the body number, but it has like a very similar kind of like distribution. So what is the problem with these two? Well, the problem is when you actually, in this case, when you want to make the prediction, is that, well, before this prediction time, you know what the gender of the passenger is. You know what the passenger class is. You have a bunch of more information about it, right? However, whether you have a boat number or a body number, that's kind of like after the prediction time, right? This is after the event actually happened. This is after after you crashed into the iceberg. So when you make the prediction, using anything that happened before the prediction time is fine. But using stuff that happened afterwards, this is kind of like the sports almanac. You can't really use this because this information is not really available at the time you want to make the prediction. So a more, less macabre and more modern example is, let's say in Salesforce you want to predict whether a lead converts to a customer. So you have a bunch of information on here, right? Like what industry is this customer in? What's the name? What is the annual revenue of this company and all of this stuff. So this is what it would look like before the conversion. Now after the conversion, it looks very similar, except now there's like a new field, deal value. And this is basically the equivalent of like the boat number, right? This field is only filled out if you actually converted to be a customer. If you didn't convert, the deal value is blank. There is no deal. There's nothing, there's no value, right? So if I tell you, well, you can use, if you just use this as a predictor in your machine learning model, the machine learning model will be very smart and say, well, if there's a deal value, you will be a big customer, right? You will become a customer. But that's not really helpful when you actually try to give that prediction to a new customer, right? So why does this kind of matter? It's great for betting. It's unfortunately not so great for machine learning. And it has a big effect on kind of like your model performance. And the model performance is obviously what eventually this is what you care about. So when you do traditional machine learning evaluation, you split up your data into training and holdout set, right? And because the model relies on information that's not actually available at scoring time, the model performance here suffers. But the problem is when you use the training and the holdout set, they're both from the same point in time, which means that your plot, when you just like plot the training and the holdout accuracy metric, whatever your accuracy metric is, you know, you'll look the same as kind of like any other plot that you will see. So, you know, you can kind of ignore the y-axis, but basically all this shows is like, well, for all of these three models, your training accuracy is pretty good, and then in the holdout, it slightly decreases or stays very similar, and then you can kind of like decide whether you want to ship this or not, right? But the problem is, this doesn't, when you have this label leakage, this doesn't really tell you anything. Because the data is from the same point in time, which means that the holdout set also has this leakage information. If I train, because you train on data from this point in time, which means they either convert or they didn't, so they have this information available. They have these leakers in there. So what you have to do now is called something that's just time-based evaluation, which is more predicting the reality of what actually happened. Which means you need to look at each record separately, and you need to score and evaluate at different times, instead of at the same time like you do in the holdout set, where you score on the holdout set and you evaluate on the holdout set. So this is a little bit more kind of like a more complicated plot, but basically what you see here is for time points T0 to T3, it doesn't really matter what they are, and you have some records. So you can see at T0, A, B, and C is your training set. They're your positive and negative examples, and D, E, and F, this is what you would want to predict, right? These are like the ones where you don't know what the outcome is. So in the traditional machine learning model, what you would do is exactly that. You would train on A, B, well, you would split up A, B, and C into like holdout and training. You would train on like, let's say A and B, and your holdout set would be C, right? And this would be like your accuracy. And then you would predict D, E, and F. So for this, however, what you would do is actually, well, let's walk through it. So at T0, what you would do is train an A, B, and C like you would before, or rather you split it up and you still do cross evaluation. And then what you do is score on D and E. So why not score on F? Well, F actually never converts. If you look at like T1, T2, and T3, you never actually know if it converts or not. So this is something where you can't run an evaluation on because you don't know the label at the end. You can, however, score on D and E. And you do that because then you can, at T1, you can actually evaluate D and E, which means you take the label at time of T1, which here in this case means D is converted and E did not convert, and you compare it to the prediction that you gave at T0. And at the same time, you now have a new row, G, which enters kind of like the business. And you can see that it's not, it's something you want to predict at T1, and it doesn't convert at T2. So you score it, and then again at T2, you can evaluate it. And you don't score, and here this is kind of one of the key things too. You can see I, which also is a new row at T1, but you don't actually score this at T1. You score it at T2. Which is kind of like the latest, this is the latest update. Something happened at T2, some field was changed. And then you can evaluate it finally at T3. So it's at each row, you basically have to check when did this, you find rows to evaluate on that weren't converted at T0 whenever you train your model, and at some point afterwards did convert. And then you basically take the latest change before this conversion. You can take a random one too, and score on that. And that ensures that there is no leakage information in there because you purposefully exclude anything that happened after the lead converted. Are there any questions on that? There's like a lot of information thrown. Does that make sense?
Do you want to train on A, B, C, D, E at the time as one?
So you don't, well, in this case, you wouldn't retrain it because you don't have to retrain on A, B, and C because they don't change. So usually after the row converts, they're kind of like stable and the rows don't really change anymore. But you could, if you have more data at T1, if you have more rows, you could retrain the model. Yeah. Okay. So, and usually now what the plot looks like of your accuracy metric is, well, at training and holdout, you kind of see a very familiar picture. Your accuracy metric will, go down a little bit or kind of stay the same. But now at evaluation, you can see this is green in the red model, the accuracy goes down a lot. And for the blue one, it doesn't. So the reason here is that for the green and the red one, those are models that had label leakage in it. And that means the model picked up on this label leakage. And in the training and the holdout set, the information was there. We knew whether there was a lead value or not. But then on the evaluation data, that value was always empty, right? So if the machine learning model says, well, if this lead value field is filled out, you're more likely to become a customer. And then all of your evaluation data, that field is empty, it will obviously bias it towards saying you did not convert, even though maybe it actually did, right? So your accuracy, you see this very kind of like massive drop in your accuracy metric. And blue, that would be kind of like one where you don't have label leakage, you don't see this massive drop in the accuracy metric. And that's obviously what you want, because when you serve this model, you want to make sure that it reflects reality of what will actually happen. And yes, so the leakers are not in the evaluation data, by definition. So how do you actually now solve this problem? And there's some solutions, and then obviously there's always more problems that you kind of realize that come along once you have some solutions. So this is some kind of data set that we would have to deal with. So you have some IDs, obviously. You have your name, address, phone, and a bunch of other columns. And now you have something that's called closed by, reason lost, amount, and then whether the lead converted or not. Just like a simple Boolean field, true, false, false, true, false. So now if you look at this, you should be able to pick out some problems with this data. So the first one is that if you look at reason lost, well, if this field is filled out, that means you always never convert it, right? This is basically some automated business that says, well, if I lost this some automated process, if I lost this lead, well, obviously it didn't convert. You lost it, for example, to some competitor. They turned you down, they went to a competitor, or for some unknown reason. If the amount is filled in, this is basically like this lead value thing, right? So if this is filled in, it means that the lead always converted, which makes sense. If you convert, there's some kind of like value associated with you. And close by is a little bit more tricky, but you can see that at least in this example, like 2 out of 3 times when it's filled out, you also convert it. Only in one of this case, it didn't convert. So this is also, it could be some automatic practice, some automated process where once you kind of like, some person goes in and closes it, this is like the ID linking to this person, and maybe some of them never get closed because you enter a lot of leads. Not all of them, for some of them you never know whether they kind of like convert or not. They might still be in your database a year after, and logically, as a human, you say, well, they're not a customer at this point because they never positively, signed an agreement. But to the machine learning model, you don't know. So The problem with this is that a lot of the times these features are simply too good. By that I mean they don't carry actually, well, when you do like statistical tests on them, they will pop up as having a really high correlation. And what we do here is we take the raw data, we generate our features, which are also usually auto-generated. For example, just like some, one-hot encoding for categorical data. Sometimes we know whether it's an email or not, so we can extract the email domain and then kind of like one-hot encode that. We can extract country codes, and then kind of like key for a lot of this is we also have a null indicator. So for every feature that we have, we add a column, or one-hot encoded column, whether this feature is null or not. And then based on that, we can calculate the correlation with the label, which would be either like Pearson's or Karamas V for categorical data. We basically calculate a threshold of what this over which threshold we will exclude all of these features and the child features. So what this means is that if there's a high correlation between whether the field is filled out or not and the label, let's say 0.9, we can say, well, this feature is a little suspicious because it has too high of a correlation, and we throw it out. We just remove it from the training set. The problem with this is obviously that once you go into something that's threshold-based, you never really know what the threshold should be. Because you obviously want to keep good features. You don't want to keep the leakers, but you want to make sure that if there's a strong signal in the data that's like has a correlation of like 0.7, this might actually be a really good feature that you want to keep. So once we kind of did this, we realized it solved a lot of the more obvious examples. If your correlation is 0.99, it's pretty obvious that, well, maybe this is something you have to either examine or just remove. But unfortunately, because the data that we deal with is really messy, it didn't actually solve everything that we had to deal with. So in this example, we have a new field, expected revenue, and you can see it's never null. It's always filled out. There's no nulls. But this is because the default value is not always null. Sometimes it's 0, or sometimes it's, I don't know, some other value. Like the customer can pick and choose whatever the default value is, and we don't know. So in this case, a value that's bigger than 0 always indicates conversion. This is basically the same thing as like these values that I've talked about before. Right? So if there's an expected revenue, then it means you did convert to be a customer. If the expected revenue is 0, it means you didn't actually become a customer, or we want to give you a prediction, probability that you actually convert. So if we just calculate the correlation now between this column and the label, there won't be anything suspicious about it, because it will treat it like a numeric feature, and it'll just give you some correlation value that's probably not really high. But what you can do is you can bucketize this. So you can basically make a histogram. And you can do this based on the data. So what we do here is we use a decision tree to auto-bucketize these features, and then you can catch them through the correlation check. So here you can see the new column added, which is the same expected revenue column after you bucketize it. It has 3 values. The third one is this null indicator that I talked about, and you can see it's 0 for all of them because, well, none of them are actually null. And the first one basically is the first bucket, and the second one is the second bucket. And here it would mean the first bucket is everything that's minus infinity to 0, including, and the second bucket is everything over 0. And here the key thing is we didn't have a data scientist go in and kind of like create these buckets. Because again, we would have hundreds of cases where you would have to figure out what these histogram buckets should be, right? So we just came up with a way where you just look at the data, the algorithm looks at the data, and auto-bucketizes it automatically. And then what happens is this is now a categorical variable. You can calculate Karamas V which is basically the same thing as, well, the equivalent of Pearson correlation. And you can then again use a threshold and say if it's above this threshold, discard this variable. And as a nice bonus, these actually work really well for model performance too. Turns out auto-bucketizing is often better than just using the actual numeric value as your feature. So far, we've really only looked at kind of like data points at one specific point in time, right? We only looked at like a static example of data. The problem is that, well, training, the data that you train on and the scoring data that you want to actually give predictions for, they're already produced at the same time. The training data is always historical because you know what the outcome is, right? You know whether the lead converted or not. But the scoring data is more recent. This is what you want to give the predictions for. No one really comes to us and says, hey, can we give us a prediction for a lead that was generated like 2 years ago? Because at that point, they don't care anymore, right? Even though theoretically, that lead could still convert and become a customer. So the problem here is that we realized there's a massive discrepancy sometimes in these leakage fields between the training set and the scoring set in terms of the fill rate. So here in the first example, you have a field that's always filled out in the training set, but it's never filled out in the scoring set. It could be something like this body number, right? It's just simply you don't have this information for all of the rows that you want a prediction for. So we looked at this and we decided, well, in that case, let's just throw out this column. Because no matter what insight you gain from this column in the training set, it's not transferable to the data that you give a prediction for, which means it doesn't actually help you at all to give a good prediction. So in the second case, we said, well, the fill rates are pretty similar, so let's keep them. In the third case, this is a little bit more interesting. We said, well, they're very similar, right? They're basically the same, but they're really low, and we also excluded it. And the reason here is that usually what we find out is that when the fill ratio is really low, there's just not enough information in them to really drive the predictive model. And I have to also call back to we have like hundreds of columns and we generate like thousands of features. So we can be pretty liberal at excluding features. This is not something where we like throw out massive information usually. And then in the fourth field, we can see that, well, again, there's a pretty big discrepancy. So we said, let's throw this out too. And this seems very counterintuitive to most data scientists because it's all about like preserving all the features, generating more features. But like I said, we have so many features that, well, first of all, this helps greatly with runtime. And also, this would just really distort your model and pick up things at training time that don't actually give you any help at prediction time. Here's another kind of like example of what we had to deal with this kind of like very messy data. So on the y-axis, you see the percentage of conversion ranging from like 0 to 1, right? And time, you can kind of ignore the month. It's just like some arbitrary time on the x-axis. And you can see that for most of the time, the conversion kind of like hovers above like 0.55, like plus or minus a little bit, right? But then in March, there's this massive spike to 1. Every single lead converted in March, which is awesome. Except it's kind of weird. Like, why, right? Why is this so biased towards positive labels? So we actually, in this case, we actually talked to the customer and they told us, well, we migrated from a different system. And we extracted all of our leads in the system and we threw out all the ones that didn't convert because we don't care about it anymore. Like why should I import a lead from 5 years ago that never converted? It's no longer relevant, right? But the machine learning model doesn't know that. And unless you have a data scientist who looks at this data, it's also not something that the machine learning will ever really know unless you tell it to. Right. So in this case, you really want to be careful to use something like the last modified date or the created date as kind of like a feature. Because that will tell you, this is awesome, everything created in March will convert, which is not actually true, right? This is not what happened in reality. So here's some kind of like to sum up this kind of like part about like why or how we exclude things, is that, well, if there's a low overall fill ratio in the training and the scoring set, we can exclude this. And by that I mean it's like a 1% rate or something. just throw it out. There's no point in kind of like keeping this field around. If there's a big discrepancy between the training and the scoring data, also throw it out, because that's a really good signal that this is some kind of leaker where you don't really have this information. What we do here is we convert the fill rates to probability distributions and compare it with Jensen-Shannon divergence. So it gives you like a nice metric where you can actually set a threshold. So this is a problem with setting thresholds, is if you calculate something where the metric varies based on the data set, it doesn't really help you. You need something that has like hard lower and upper bounds. And the third point was that, well, some dates can really skew things. And you want to really be careful about using date features that might be biased towards either positive or negative as a feature. And the awesome thing about this, compared to the part where I talked about the correlations, is that this, you don't actually need to do any feature transformations on this, right? You don't need to do one-hot encoding. You don't need to do anything. You can just use the raw columns that you get, the raw data, and it's much, much quicker to actually do this. Your feature generations, they will influence like your correlations, obviously. Here, it doesn't actually matter. You can just throw anything at it. You can generate fill rates for anything, right? So what does this look like at an actual use case that we had? So here we compared this AutoML, the auto machine learning, with kind of like these thresholds that we had, to a data scientist who spent, I think, like 1 or 2 weeks hand-tuning a model and mostly looking at, okay, give me all the 800 fields that we have in this model. I'm going to go through each one and look at this data like manually and see whether I should exclude it or not. So the AutoML removed 73 fields. The data scientist removed 42. And you can see in this Venn diagram in the middle, that's the overlap. So the good thing is the data scientist definitely found some things that the auto machine learning also did. The machine learning found a lot more. But you can also see that there are some that the data scientists removed that we didn't find with the auto machine learning. And that's because, well, the examples I showed you are kind of like the more straightforward ones. Some of them are a little bit more tricky, right? When you set a threshold, let's say the threshold is 0.7. So now you might have a field that's like 0.69. And you're like, well, I guess that's not getting thrown out, but maybe it should, right? So usually what we do is once we have a data scientist look at this, we look at all of these fields and try to come up with general mechanisms and methods to throw these fields out. It's not always successful, but often it works. That's how we kind of like came up with all the other methods. So just to kind of like sum up this quickly, and to kind of like give some final thoughts. So one of these problems that I've talked about is the threshold problem, right? And this is really because we have to solve for all customers. We are a machine learning platform, which means that we don't actually, we want to really make pipelines for all the customers that we have. We can't, have a data scientist pick and choose the threshold for every single model. But we have to find kind of like, we have to find some thresholds that work the best for the majority of the models, even if it means that maybe 1 or 2 models might have a better solution, right? Obviously, I forgot the first part, but in general, it's just really tricky to choose. When you think about correlation, you have to set the threshold somewhere, but you don't want to go too low because then you're throwing out really good predictive features, right? And in fact, when people uploaded, some customers, they wanted to test this, and they uploaded like Kaggle data, and we threw out basically everything. Because there was like biology data or something, and there were like some really strong predictors in there, but the correlation was like 0.95. And that's what, is really good when you know that this isn't a leaker. But because we deal with enterprise data, we usually can't assume that. And because it's really hard to kind of like choose this threshold, what we try to do now is to do these smart decisions based on the data and the data shape. So instead of setting a threshold, we want to do something like auto-bucketizing, right? Maybe don't go in and like tell the, let's use these buckets. We just say, let the algorithm figure it out what the buckets should be based on the data, and basically let all decisions be made by machine learning. And this also means there's lots of experimentation of trying out different thresholds, different configurations, and different ways of catching this. And to learn kind of like these, so both to kind of like, yeah, fine-tune the thresholds, and also just to kind of like learn some more heuristics that we can then translate into machine learning algorithms. So the key takeaways here is that enterprise data is very messy, and you should be very careful of just like throwing your standard machine learning pipeline at it. We often have this like label leakage, and too good to be true is a problem. When all of your models that you produce have like accuracy metrics of 0.99, you should probably look at it again and not quite trust it. And you can't just like use the normal evaluation of training and holdout, cross-validation. It doesn't work if the data that you evaluate on also has this label leakage. So you can't actually, this is the very annoying part, is when you first ship a model, you can't do this time-based evaluation. You don't have like 3 months of future data. So you kind of have to trust your model there. And you kind of like, even though the methods that are described here are relatively straightforward, they were all pretty novel on how to apply this for label leakage. And we're still kind of working on some more advanced methods to catch these things. So the good thing is that now you obviously all want to try this out. The good thing is we have an open source library, Transmogrify. It's built on top of Spark ML. It's a full machine learning pipeline. Both of these things that I talked about, kind of like comparing the training and the scoring set, and excluding things based on correlations. This is both part of this. Probably takes you about 10 lines of code to do all of this, what I talked about. And if you're interested more, go to the GitHub page. There's a lot of stuff on there that you can learn about. And we're also hiring more data scientists. We're actually also hiring more data engineers and more full stack engineers. So whatever you are, if you're interested in, come talk to me. And yep, that's it. Thank you very much for listening. And if there's time for questions, let me know. You have a few minutes, so yeah.
So when you're doing something like flow rate or training and scoring sets, it's really easy to do when you have the training and the scoring sets at the same time, but what if I just have the training set? How do you dynamically drop these back into an uncertain prediction?
Yeah, so the question was, what if you don't have the scoring time? How do you do the comparison between the fill rates? And yeah, the answer is you can't. The good thing is that in our use case, we always have the training and the scoring set. So that's not something we had to solve. And that was, but it was something that it took us a while to kind of realize that we had that advantage, because usually you don't have it. Yeah.